Have a nice time, Tom. Today our topic of discussion is RSA Cryptosystem. Suppose Alice wants to send a secret number to Bob. What she will do is she will encode the number using some mathematical key and send the message to Bob. Bob knows how to decode it using some other mathematical key. So this will keep the privacy of the message. So today we will study how to construct the mathematical keys for encryption and decryption using RSA Cryptosystem. First, let us have an example. Consider the set M is equal to set 0, 1, 2, 3, etc. 14 and consider the function from M to M given by f of x equal to x cube over 15. That is, the remainder obtained from the number x cube is divided by 15. So these are some values of the function given. From if x is equal to 0, we have x cube and divided by 15, remainder 0. So if you have 3 cube is 27. 27 when divided by 15, the remainder is 12. Likewise, we have constructed the values of x and f of x here. The question is, if you know x, you know how to calculate f of x. Now suppose you are given the value of f of x for a particular x. Can you predict the value of x such that f of x is equal to 13? So here by inspection you can see that the same function works to the inverse part also. That is, for example, if you have 2 cube is 8 when divided by 15, the remainder is 8 itself. And you have if f of x equal to 4, then you can take 4 cube is 64 when divided by 15, the remainder is 4. So the same rule is working from x to f of x and from f of x to x. Or we can see that f of x equal to x itself. This concept is actually working behind RSA Cryptosystem. Actually, you have to construct some f and you have to find the function g such that g of f of x becomes x itself. So let us go to the theoretical part. First, let us explain what is meant by RSA Cryptosystem. In RSA Cryptosystem, actually we choose two gigantic prime numbers, p and q, and let n is equal to p into q, the product of the primes p into q. And we use this p and q to find the numbers e and d such that f of x equal to x raised to e over n and g of x equal to x raised to d over n. And the circuit point is that g of f of x becomes x itself. That is, x raised to e over n raised to d over n equal to x itself. That is, we are finding then x raised to e, then we divide the number by n and find the remainder. Then we take to the power d, again divide by n and find the remainder. Then the answer becomes x. So the encoding part is, the encoder will find x to the power e and find the remainder when divided by n. That is sent to the receiver, and he will find dth power of what he received and find the remainder when divided by n. That becomes the actual message. Here n and e will reveal to the public. To encode the number, the encoder must know what should be the power e that he has to do, x raised to e. Okay? So n and e will reveal to the public, but p, q and e will keep secret. And the security lies in the fact that it is very difficult to factorize a number into p into q. If the number is very big, it is very difficult to factorize this as product of primes. Now let us prove a result. X to the power ed over n equal to x to the power n over n to the power d over n. So first we write x to the power e as q into n plus x to the power e over n. That is, when we divide x to the power e by n, q is the quotient and this part is the remainder. Remainder, actually you are giving this notation. And what becomes x raised to e into d, that is qn plus x to the power e over d Let us prove the congruence for P. Case 1, if P divides X, that is X is a multiple of P, then X congruent to 0 mod P. That is when X is a multiple of P, when X is divided by P, the remainder is 0. And you will take, here it is plus 1. We are taking K into P minus 1 into Q minus 1 plus 1 to the power of X. Then that is congruent to 0 to the power K into P minus 1 into Q minus 1 plus 1. That is again 0. So it's congruent to 0 mod P. And you know that 0 is congruent to X mod P. So you can write here as X raised to K into P minus 1 into Q minus 1 plus 1 is congruent to X mod P. Now case 2 is P doesn't divide X. P is a prime and that is not a factor of X. Means that greatest common divisor of X and P equal to 1. That is, there is no common factors for P and X. The only common factor is 1. Therefore, by Fermat's theorem, you know X to the power phi of P is congruent to 1 mod P. And phi of P is P minus 1. Phi of P means that number of primes less than P and relatively prime to P. So the number is P minus 1. So we have the relation X raised to P minus 1 congruent to 1 mod P. So therefore, X raised to K into P minus 1 into Q minus 1 congruent to 1 raised to K into Q minus 1. It is congruent to 1 mod P. And we are multiplying X to both sides. We will get the result. So we have the result X to the power K into P minus 1 into Q minus 1 plus 1 is congruent to X mod N if N is equal to P into Q. X is any integer and K is a natural number. Now we are going to the procedure of RSA Cryptosystem. We will use the previous results to fix capital N, E and D in RSA Cryptosystem. The procedure is, so we select two gigantic primes P and Q and the product is taken as capital N. And using P and Q, you have to find the number E and D. The requirement is the decoder will find X to the power E over N and will send to the receiver, and the receiver will decrypt this as, if it is capital Y, he will find Y to the power D over N and the answer becomes capital X. So this is a procedure working in RSA Cryptosystem. So we choose a number P and Q such that capital N is equal to P into Q. Then what will be phi of N? Phi of N is, by formula, it is N into, that is P into Q into 1 minus 1 by P into 1 minus 1 by Q. So that's equal to P into Q into 1, P minus 1 by P into Q minus 1 by Q. That is 1 minus P into, P minus 1 into Q minus 1. Now let E be a number relatively prime to P minus 1 into Q minus 1. That is the way in which E is selecting. Okay? E is a number relatively prime to this phi of N. So that means that GCD of this E and P minus 1 into Q minus 1 equal to 1. So if GCD of two numbers equal to 1, you can find the numbers lambda and mu satisfying this relation. That is lambda into P minus 1 into Q minus 1 plus mu into E equal to 1, because this P minus 1 into Q minus 1 and E are GCD 1. Now we can select this mu in a particular way that 0 less than mu less than P minus 1 into Q minus 1. So let me go to the theoretical part again. For example, let n and n be two integers such that GCD of n is equal to 1. So there it is integers lambda and mu such that lambda into n plus mu into n is equal to 1. So the result here is we can choose this mu such that mu is less than n. And suppose what happens if mu is greater than n. Okay? So it becomes lambda m plus, if mu is greater than m, you can divide mu by m and mu can be written as some portion into m plus some remainder, let it be mu dash. So into n is equal to 1. Okay. I am combining the terms with m and we can write this as some lambda dash into m plus mu dash into n is equal to 1. Now we can say that this mu dash is less than m, because mu dash is the remainder obtained when mu is divided by m. Hence, we can choose mu such that 0 less than mu less than P minus 1 into Q minus 1, because here GCD of p minus 1 into q minus 1 and e equal to 1, and lambda and mu is chosen in such a way. And since this e and mu are integers greater than 0, what happens to this equation? This 1 minus mu e becomes negative in the right hand side. And you know p minus 1 is positive and q minus 1 is positive. So this lambda must be negative. This implies lambda less than 0. And we call minus lambda as k and this particular mu as d. D is an integer we want to decode the message. Then what happens to this equation? This becomes, I am taking this minus mu e to this side and this lambda into p minus 1 into q minus 1 to this side. And what I get is k into this minus lambda becomes k into p minus 1 into q minus 1 plus 1 equal to d into e. Actually, we want to show that when we choose when we choose e and d in this way, then x raised to e over n to the power d over n equal to x itself. So here x raised to e over n to the power d over n equal to x raised to e into d over n. This result we have proved earlier, and this is equal to x raised to k into p minus 1 into q minus 1 plus 1 because de equal to this one. Okay, and we have already proved that when we divide this expression by n, remainder becomes x. That is proved as a proposition. So what we proved is, if you have a number x, you just find x to the power e, then divide the number by capital N, find the remainder, then take that number to the power d, again divide the number by n and find the remainder, it becomes x. So this is the theory working behind RSA Cryptosystem. Now let us illustrate the process using a problem. Suppose capital N is equal to 5 into 7 is two of prime numbers and the product is 35. Phi of n is equal to p minus 1 into q minus 1, that is 24. We have to choose the number e which is relatively prime to 24. I choose it as 5. Now GCD of 24 and 5 is equal to 1. Therefore by Euclidean algorithm I can write 1 is equal to minus 1 into 24 plus 5 into 5. To prove, we have shown that this number lambda becomes negative. And we choose the number 5 as our number d. And you can decode you can encrypt any number from 0 to 34 using this process because we have taken capital N as 35. So I can encode the numbers from 0 to 34. For example, if I take x equal to 3, e equal to 5. So we will find 3 raised to 5 and we'll find the remainder obtained when it is divided by 35. So that's equal to 33. So we decode the number 3 as 33. And the receiver will find 33 raised to 5 because d equal to 5 here. So 33 raised to 5 when divided by 35, remainder is 3, which is x itself. So this is the process of RSA cryptosystem. So the security of the system lies in the fact that it is very difficult to find the prime factors of a number. Even RSA Labs has put forward several factoring challenges. The hardest unsolved challenge is one in which a 617 digits number, capital N, is given, and you are asked to factorize the number as p into q. And if you can find the factors p and q, you will be able to claim the $2 lakhs prize money. And this shows that it is very difficult to factorize a number into its prime factors. And in the coming classes, we will discuss some algorithms which are available to find the prime factors of a number. Thank you.